Have you ever sat in math class, staring at some ridiculous question, and just thought, what's the point of this? Like, seriously, who cares how fast the train leaves the station, or why you're solving for x again? In math class, there's always that one kid who asks the teacher, when am I ever going to use this in real life? And honestly, it's a fair question. Because for most of us, math ends when the bell rings. But what have I told you? Math problems could be your ticket to riches. That there are questions out there so difficult, actual mathematicians are dumbfounded by them, and that whoever solves one can earn a prize of $1 million for a single problem. This is the extreme reality of the Millennium Prize problems. Not just one simple math question, but 7 of the hardest questions ever created by humans. Each one is worth $1 million, with only one ever being solved. These aren't just random math puzzles though either. They deal with the deepest parts of our world: computers, physics, and even the structure of the universe itself. Today we're breaking down all 7 of these so-called impossible questions, what they mean, why they matter, and the story of the one man who actually solved one, and why he refused the fame and money that came with it. The Millennium Problems were announced in the year 2000 by the Clay Mathematics Institute. Their goal was to highlight the biggest unsolved questions in math, the kind of problems that, if cracked, could completely reshape science and technology. Like mentioned before, each problem comes with a $1 million prize, yet the real reward isn't money. But to be completely honest, not gonna lie, for someone like me,
Tell them to bring me my money.
for mathematicians in all seriousness, the true prize is the immortality it brings in the world of mathematics. But what are these impossible 7 problems? Problem 1 might sound abstract, but it's actually about computers and possibly the future of AI. The question asks, if a problem is easy to check, does that mean it's also easy to solve? Think of Sudoku. Once you see a completed grid, it's easy to check if it's right, but solving it from scratch can take hours. P versus NP asks whether every problem that's quick to verify can also be solved quickly by a computer. If the answer were yes, if P equals NP, that would mean encryption, passwords, and most of modern cybersecurity would collapse overnight. Every secret code could be broken instantly. Every hard problem could be cracked. But if P doesn't equal NP, it means there are limits. Things computers can never do, no matter how fast they get. It's one of the most important open questions in computer science. Problem 2 asks to imagine fluids. Water, air, smoke, and even blood? We have equations that describe how these things flow, called the Navier-Stokes equations. But the catch is that we don't actually know if they always make sense. Sometimes these equations predict that fluid can blow up, turning into mathematical nonsense and infinite values. The problem asks whether smooth, stable solutions always exist, or if fluids can truly behave chaotically at a fundamental level. Solving this could revolutionize everything from weather prediction to aircraft design. Right now, the math behind how a wave breaks, or how a tornado forms, is still a mystery. Problem 3 is probably the most famous one. The Riemann hypothesis is about prime numbers, which are numbers that can only be divided by 1 and themselves. Primes are like the atoms of mathematics, and the Riemann hypothesis predicts how they're spaced out among all the numbers. It's based on something called the Riemann zeta function, and we're not going to worry about that detail. Just know that if it's true, it means there's a hidden pattern and what looks like total randomness. Proving or disproving it could completely change number theory and affect encryption systems that protect the entire internet. Problem 4 is the Yang-Mills theory, which is basically the math behind the fundamental forces of nature, the forces that make up particles, atoms, and everything else in the universe. The mass gap part means that the particles this theory describes should have positive mass, even though the equations seem to say that they shouldn't. So mathematicians are asked to prove that the theory actually works as it does in real life, to show that the math produces stable particles. If solved, it would tighten the link between quantum physics and mathematics, and maybe even help unify the forces of nature someday. Problem 5 is pure geometry and algebra. The Hodge conjecture asks, if you have a complicated shape, like a weird curved surface in many dimensions, can you always describe it using simple algebraic equations? It's about the connection between how things look in geometry and how they can be expressed in algebra. Think of it like asking whether every mountain, every curve and bump in the world has a perfect mathematical formula behind it. A proof here would bridge two of the biggest branches of math and help us better model space, shapes, and even the universe itself. Problem 6 sounds deceptively simple. It asks, if a shape has no edges, no holes, and every loop on it can shrink down to a single point, is it just a sphere? That's obvious in 2D. A balloon is a sphere. But in 3D space, it's insanely complicated. For over 100 years, no one could prove it. It sat there mocking mathematicians, until one person came along and actually cracked it. The 7th and final problem ties together algebra, geometry, and number theory. It deals with elliptic curves and equations that look simple but hide deep patterns. These curves are the foundation of modern cryptography, basically how your data stays secure online. The conjecture tries to describe when these curves have a finite or infinite number of rational solutions. If someone solves it, we could understand encryption at a level we never have before, or break it down entirely. This is Grigory Perelman. In 2003, this Russian mathematician quietly uploaded a series of papers online. His work claimed to solve the 6th mentioned problem, the Poincare conjecture, one of the hardest problems ever attempted. But he didn't start from nothing. His proof was built on the ideas of Richard S. Hamilton, an American mathematician who, back in the 1980s, developed something called Ricci flow, a process that smooths out the shape of space like heat spreading over an object. Hamilton's idea was brilliant, but the equations kept breaking down when they hit singularities, points where the math went infinite. Perelman built on Hamilton's foundation and fixed those issues. He introduced new tools, an entropy formula, a reduced volume concept, and something called the no local collapsing theorem, all of which made it possible to finally finish what Hamilton started. Together, the ideas proved something even bigger than the Poincare conjecture, the geometrization conjecture, which describes how all three-dimensional spaces can be classified. By 2006, mathematicians had confirmed that Perelman's proof was correct. The Clay Institute offered him the $1 million Millennium Prize, and he was also awarded the Fields Medal, the highest honor in mathematics. But Perelman refused both. Part of the reason was simple. He believed Richard Hamilton deserved equal credit, and he didn't want to accept a prize that ignored the foundation it was built on. He also said he didn't trust the mathematical community's fairness. In one interview, Perelman said, "I'm not interested in money or fame. I know how the universe is built." After that, he stepped away from mathematics completely, living quietly in Russia, turning down everything that came with his discovery. So what's next? Most experts think the Riemann hypothesis is the closest to being solved. It's the backbone of number theory, the math that underlies prime numbers, cryptography, and digital security. The P versus NP problem might fall first, especially as artificial intelligence and quantum computers evolve. The Millennium problems remind us how much we don't know and how much more there's left to discover. One man, working essentially alone, managed to solve one of the hardest problems ever known. Maybe the next person will be some quiet genius no one's ever heard of. Or maybe it'll be someone watching this video right now. Who am I kidding? We are not smart enough for this. We, me and you. Either way, 6 mysteries remain, and they're still waiting for an answer. Bye. Yep, feel free to comment on what you'll, want to see me do a vid on next. Obviously, it's not very good. I actually made this because I was just messing around making something, and then my girlfriend was like, "Can you explain that to me?" So I made this whole video to explain something to my girlfriend. So hopefully that goes along well, but if it ends up doing semi-alright, I might just do more anyway, but yeah, feel free to comment what you want to see me do. Yeah. That's all.